Suppose you are driving your car and suddenly your car runs out of petrol. My question is, how much force would you need to accelerate your car to a certain speed? The answer to this is quite simple. You can answer this using Newton's second law. Force equals mass times acceleration. This wonderful equation describes all types of motion classically quite well. But when humans first started observing things on a small scale, like how an electron orbits the nucleus, how an electron behaves, then we found that Newton's laws do not apply at this length scale. To describe the tiny world, we needed another kind of mechanics, which was named quantum mechanics, and the equation that describes the laws of quantum mechanics. Just like Newton's second law, in the quantum world, the equation that is analogous to Newton's second law is called the Schrödinger equation. Well, what is the Schrödinger equation and what does it want to tell us? Today we will discuss this in full detail. See, in classical mechanics, to describe the state of any physical system, we use two things. First, its position, and second, its momentum. But why do we actually need position and momentum to define any system? The answer to this is quite simple. Classically, once you calculate the position and momentum of an object at a given time, you get all the information related to that object, such as what its velocity will be, what its energy will be, and many other things as well. But as soon as you move to the atomic scale, to the quantum scale, things don't behave the same way. Suppose you confine a tiny particle inside a box at the quantum scale, then in such a case, force equals mass times acceleration won't work there. You want to know what the position of the particle is inside the box and what its momentum is. But you won't be able to know both of these things exactly at the same time. Here, you encounter Heisenberg's uncertainty principle, which, in short, tells us that you cannot measure the exact position and exact momentum of a quantum particle at the same time. Anyway, the uncertainty principle is quite an interesting topic in itself. I will talk about this in full detail in a separate video sometime. But inside that box, you cannot determine the exact position and momentum of that particle. But if it were a classical particle here, then you could accurately measure its position and momentum. Why? Because to describe the state of a classical system, position and momentum are perfectly accurate and correct variables. But when we talk about quantum mechanics, so the uncertainty principle prevents us from choosing these variables. This means that position and momentum are not the correct variables at the quantum scale. Even though the uncertainty principle prevents us from measuring position and momentum to describe our system, we have created some new variables to study quantum mechanics. In quantum mechanics, to define the state of a system, we use other things such as its energy levels or its wave function. And this wave function describes your entire quantum system. For this reason, if you have studied quantum mechanics before, you would know that when solving any system, we are mostly concerned with its wave function and energy levels. We want to calculate them correctly, and then, using these, we describe the entire state of the system. The Schrödinger equation provides us with the solutions for these wave functions and energy levels. Now, there is one more thing here. Classically, whenever we study any system, we always consider them as particles. But throughout history, there have been many philosophies suggesting that the electron is not entirely a particle. I mean, there has been a long-standing debate in history regarding the nature of the electron, whether it is a particle or a wave, and the conclusion of this debate was that in reality, it has a dual nature. Anyway, going into that debate is not our topic right now. We will discuss that some other time. But because of this dual nature, in quantum mechanics, Schrödinger used wave mechanics to describe the electron. That is, he considered the electron as a wave. He applied the wave equation to it. So the equation we're about to discuss is actually Schrödinger's time-independent equation. That means we won't be discussing how the state of the system changes with time here. Here, we'll only talk about the time-independent Schrödinger equation. Now, there are actually many ways to understand the Schrödinger equation, and I have already made a video on this before. But today, we'll understand it by taking an example. Particle in a box. Suppose you have a quantum system and you confine an electron inside a box. You want to know everything about that electron. So what do? We make predictions about where it could be, what its energy level might be. Well, all these answers are contained within our famous Schrödinger equation. So let's look at the different terms present in this equation one by one. First of all, the most important term, c, is what we call the wave function. In simple terms, the wave function simply tells us where the electron could be, but it doesn't tell us where the electron actually is. In fact, there's a difference between the two things, where it could be and where it actually is. When you say where it could be, you're talking about chances, probability. But when you ask where something is, you're talking about its exact position. The wave function doesn't tell us the exact position. Instead, it tells us the chances. See, quantum objects are very clever. You can't say exactly where it is unless you measure it. You can only talk about its probability. Suppose I lock my friend in a room and I have to predict what he might be doing inside the room. So, because I know what my friend's nature is like, I can say that there is a 50% chance that he is sleeping. There is a 25% chance that he is watching Instagram reels on his phone. There is a 15% chance that he is studying and a 10% chance that he is talking to someone. But until I open that room and see for myself, I can't say exactly what he is doing. But at any given time, he is doing only one thing. Quantum particles do exactly the same thing. So when you trap a quantum particle in a box and you have to guess where the electron is inside the box, the wave function tells us just that. It gives us the probability of where the electron could be. But the big difference here is that when my friend was trapped in the room, at any given time, he was only doing one thing. But electrons don't behave like that. Electrons will exist in all possible places at the same time. Why is that? Because the electron will behave like a wave and through wave superposition will be spread out across the entire box. And this exact same thing is explained to us by a famous thought experiment called the Schrödinger's cat experiment. So in this act, we don't know where the electron is. This helps the probability distribution to spread out, like a wave, and different types of waves represent different probabilities of where the electron could be. That's why it's called a wave function. Now, as soon as you make a measurement, that is, you open the box to see where the electron is, this probability wave that was spread out collapses and we get the probability at a particular point, indicating the chances of finding the electron there. This phenomenon is what we call the collapse of the wave function, and this is exactly what describes the dual nature of the electron. When you haven't observed it, it behaves like a wave. But as soon as you observe it, its wave function collapses and you get the probability. Now there's one more thing here. The PSI, or the wave function itself, doesn't have any significance. I mean, it doesn't have any physical significance. But psi squared, that is, when you square the wave function, it gives us the probability amplitude. So actually when we talk about probability, we're really referring to PSI squared. Now, let's talk about the second term. This actually represents energy. That is, what possible energies the electron can have. Now, what exactly do I mean by which energies? It's not true at all that an electron can have any energy. At the quantum level, a particle actually has fixed energies, and these energy levels are obtained by solving the Schrödinger equation. But in a classical system, your particle can have any energy. It can take on continuous energy values. However, quantum particles exist at discrete energy levels, and the reason for this is that our probability distribution has a wave-like nature. You can understand it like this. Since our electron is inside a box, it means that the waves of the electron inside the box can only exist up to the boundaries of that box. There is zero probability of finding the electron outside the box. In fact, here we have imposed a boundary condition for this system that the electron can only be confined inside this box. It cannot go outside. This means that at the boundary of the box, our wave function must always be zero. If it is not zero there, then it means that our electron is also present outside the box. And we know that this is not the case. This means that the electron can only have certain frequencies. Now, where did frequency come into the picture here? Because the electron is a wave, and waves have frequencies, this means that only those frequencies will be allowed where the wave function is zero at the boundaries. So only these frequencies can be allowed. Or this frequency can also be allowed, and this frequency can also be allowed. But this frequency cannot be allowed. And by that time, Einstein had also figured out that energy is proportional to frequency, equal to hnu, in his famous explanation of the photoelectric effect. In E equals hnu, h is a constant which is called Planck's constant. Here, nu represents frequency and E represents energy, and in this example, we know that only those frequencies are allowed which make the wave function zero at the boundary. This means that only certain energy levels are allowed inside our box, and these are the discrete values of energy, that is, quantized values. It is because of these quantized values that this branch of mechanics is called quantum mechanics. Quantum means quantized, that is, discrete. Whenever you look at different systems in quantum mechanics, such as the particle in a box, the harmonic oscillator, the 3D box, or any other system, only certain energy levels are allowed in them. Which energy levels are allowed and which are not, we find the expression for this by solving the Schrödinger equation. Now see, we have learned two things from this equation, the energy levels and the wave functions, which are on the left-hand side of the equation. There are also two terms on the right-hand side, but the important thing to note is that we want to solve the terms on the left-hand side. So it means that if you solve the things on the right-hand side, you get the energy levels. If you have the energy levels and the wave function, then we can figure out everything else about the particle. Just like classically we find the position and momentum of things. See, we know what the total energy of our system is. Kinetic energy plus potential energy, so the equation written on the right-hand side actually represents the total energy of our system. So the term with V represents the potential energy of the wave function, and the other term represents the kinetic energy. Now why is the second term kinetic energy? There is actually a very beautiful derivation behind this, which you can look up and read on the internet. So now, if you solve both terms on the right-hand side, you will get the energy levels of the system. And for information about our electrons, this is all we need. So if we talk about the particle in a box, the solution to its wave function looks something like this. Equal to under root 2 upon L sine n pix upon L, and the energy equation comes out to be h bar squared n squared pi squared upon 2ml squared. And if you write h bar squared in terms of h, it becomes n squared h squared upon 8ml squared. Now here, see, pi is a constant, m, which is the mass of the electron, is also a constant. L is the length of the box, which is also a constant. H bar is also a constant. And what is N is the different states of the electron, 1, 2, 3, 4, and so on. If you change the value of N, you will get different energy levels. That means here, the energy has quantized values, there are different energy levels, and the wave function here tells us where the electron is. So here, I have created a Python program. So if you put n equal to 1, the form of the wave function will look something like this. Here you can see that at the boundary of the box, its probability is 0 because our particle is confined inside the box. If you change the value of n, you will get different wave functions, which will represent different energy levels. That is, they will represent different frequencies. But one thing will always remain common. At the boundary, our wave function will always be 0. Here's another thing. Why is our wave function 0 at the boundary? Because at the boundary, as I showed on the right-hand side with the potential energy term, the value of V for a particle in a box is infinite at the boundary. This means that our electron does not have enough potential energy to cross this barrier. So in different systems, the value of this potential changes. For example, in the case of a free particle, the potential will be 0. So you can create a program and give me the representation of its energy levels and wave functions. My email ID is jh5robin@gmail.com. In the same way, you can solve the harmonic oscillator, you can solve the three-dimensional box, and similarly, you can solve different systems like this. Now, if you look at the Schrödinger equation in its expanded form, you can see here the terms del squared upon del x squared plus del squared upon del y squared plus del squared upon del z squared. These are actually coordinates in space, meaning they represent position. So, when you substitute different position values into the Schrödinger equation, you get the probability of finding the electron at that particular point. Similarly, when you substitute many such values, meaning you plot many probabilities on a graph, you find that at some places, the probability of finding the electron is quite high, while at other places, the probability is absolutely 0. The places where the probability of finding the electron is 0 are called nodes. In this way, when you plot this graph for different positions, you get the shapes of orbitals, s orbital, p orbital, d orbital, and so on. So, in practical cases, what Bohr said, that the electron revolves around the nucleus in a fixed orbit, is not actually true. And actually, it's just a probability cloud that we get by solving the Schrödinger equation, because an electron isn't exactly a particle, it's a wave. We only get the probability of its position when we solve the Schrödinger equation. When you solve the Schrödinger equation, you get the probability of finding the electron at a particular point, how likely it is to be there. That's how we get the shape of the orbital. We'll also solve the Schrödinger equation mathematically, but maybe in another video. For now, let me know how you liked this video. Please like it, share it with your friends, and if you haven't subscribed to our channel yet, do subscribe so you don't miss any future videos or updates.